Bismillahirrahmanirrahim. I am Dr. Javed Ali, Assistant Professor, Department of Chemistry, Cust. Welcome to the course Physical Chemistry 2. Course code is 332. Today's topic is kinetics of second order reaction with different initial concentration of reactants. Outline of the topic: Introduction to second order kinetics with different initial concentration of reactants, mathematical equation and data interpretation. Examples of second order reaction. In the second order reaction, when initial concentration of reactants are different, then the rate of reaction is proportional to the sum of the both reactants concentration raised to the power unity. The second order reaction can be expressed as A plus B is going to the product, where A represent reactant A and B represent another reactant B. The rate law for second order reaction when initial concentration of reactants are different is dP divided by dt is equal to K, concentration of reactant A and concentration of reactant B. dP divided by dt represents the rate of formation of product or change in concentration of P with respect to time. Rate of the reaction is proportional to the sum of the both reactant concentration raised to power unity. So, the second order reactions when the initial concentration of reactants are different can be represented by dx divided by dt is equal to K, concentration of reactant A and concentration of reactant B, where X is concentration of product, A is concentration of reactant A, B is concentration of reactant B. T represent time and K represent rate constant. So this equation, in this equation A and B are reactant concentration, K is constant, dx divided by dt represent rate of formation of product or change in a concentration of product with respect to time. We can also write this equation in the below form as dx divided by dt is equal to K A naught minus x and B naught minus x, where A naught represents initial concentration of reactant A and B naught represent initial concentration of reactant B, and x represent the concentration of product. We know that A is equal to A naught minus x and B naught minus x is equal to B. So we can rearrange this equation minus dx divided by dt is equal to K A naught minus x and B naught minus x to dx divided by A naught minus x and B naught minus x is equal to K dt by shifting A naught minus x and B naught minus x to this side and T and dt to another side. Now to convert this equation into integrated form, we need to take integration of this equation. By taking integration, we get integration of dx divided by A naught minus x and B naught minus x is equal to integration K dt. The equation can be solved by partial fraction method as is we know 1 divided by a naught minus x and b naught minus x is equal to p divided by a naught minus x plus q divided by b naught minus x, where p and q are constants. To find out the p and q value, we can rearrange this equation by multiplying a naught minus x and b naught minus x with both sides. So a naught minus x and b naught minus x will cancel 1 divided by a naught minus x and b naught minus x. And this side, the a naught minus x and b naught minus x will cancel with a naught minus x, and the only terms, the remaining term will be b naught minus x. And similarly q and a naught minus x, because b naught minus x will cancel with b naught minus x. So we will get the equation 1 is equal to p into b naught minus x plus q a naught minus x. By putting x value is a naught, we can get the value of p. When we put x is equal to a naught, so the a naught, this term a naught minus x will equal to 0, because a naught minus a naught is equal to 0, and q multiply with 0, so the whole term will equal to 0. So now the equation will become 1 is equal to p b naught minus a naught, because x is equal to a naught. And by rearranging, p is equal to 1 divided by b naught minus a naught. Similarly, to find out the q value by putting x is equal to p, we can get the q value. When x is equal to b, b naught minus b naught is equal to 0, and p multiply 0 is also equal to 0, so we can cancel this term. By putting x value is equal to b naught, we get 1 is equal to q a naught minus b naught, because x is equal to b naught. By rearranging, q is equal to 1 divided by a naught minus b naught. Finally, substituting the value of p and q in the above equation, we get 1 divided by a naught minus x, b naught minus x is equal to 1 divided by b naught minus a naught and a naught minus x, because 1 divided by b naught minus a naught is value of p, plus 1 divided by a naught minus b naught into b naught minus x is 1 divided by a naught minus b naught is value of q. Now multiply both sides with dx. So the equation will become dx divided by a naught minus x into b naught minus x is equal to dx divided by b naught minus a naught into a naught minus x, plus dx divided by a naught minus b naught into b naught minus x. Now we can rearrange b naught minus a naught to a naught minus b naught, because here is also a naught minus b naught, and if we rearrange b naught to a naught, so we can take a naught b naught and a naught b naught common from the both terms. Therefore, the equation will become dx divided by a naught minus x b naught minus x is equal to minus dx divided by a naught minus b naught into a naught minus x, because b naught minus b naught minus a naught is equal to minus into a naught minus b naught, so we can write the minus sign here, plus dx divided by b naught minus x into a naught minus b naught. Now take a naught minus b naught common from both sides. We also know dx divided by a naught minus x into b naught minus x is equal to k dt. And we can take a naught minus b naught from both terms. We will get the final equation, which is 1 divided by a naught minus b naught into minus dx divided by a naught minus x plus dx b naught minus x is equal to k dt. Now to solve this equation, take integration of both sides. By taking integration, the equation become 1 divided by a naught minus b naught into integration of minus dx divided by a naught minus x plus integration of dx divided by b naught minus x is equal to integration of k dt. K is constant, so we can take k out from integration and k integration dt. So by solving this equation, as we know, integration of dx divided by a naught minus x is equal to minus log a naught minus x, and minus log will cancel each other. Similarly, integration of dx divided by b naught minus x is equal to minus log b naught minus x, and integration of dt is equal to t. So by solving integration, we get this equation: 1 divided by a naught minus b naught into log a naught minus x minus log b naught minus x is equal to kt plus z. We know log a naught minus x minus log b naught minus x is also equal to log a naught minus x divided by b naught minus x. So we can rearrange this equation. So we can write this equation as 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x is equal to kt plus z, where z is integration constant. The value of z can be determined by applying initial condition of reaction. When t is 0, then x is also equal to 0. By putting t is equal to 0 and x is equal to 0 in this equation, we will get 1 divided by a naught minus b naught log a naught divided by b naught is equal to z, because kt will become 0 and x is 0, so a naught minus x will equal to a naught and b naught minus x will equal to b naught. So now this is the z value. By putting z value in the equation, we get 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x is equal to 1 divided by a naught minus b naught log a naught divided by b naught plus kt, where 1 divided by a naught minus b naught log a naught b naught is value of z. This is integrated form of second order equation when initial concentration of reactants are different. This is a straight line equation where this term 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x is dependent variable and t is independent variable. Therefore, we can plot 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x versus t. We will get a straight line equation with positive slope, we will get a straight line equation with positive slope equal to k, and the intercept will equal to 1 divided by a naught minus b naught log a naught divided by b naught. So we can rearrange this equation by shifting this term to this side. Now the equation is 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x minus 1 divided by a naught minus b naught log a naught divided by b naught is equal to kt. We can further simplify this equation by taking 1 divided by a naught minus b naught common, and log a naught minus x divided by b naught minus x minus log a naught divided by b naught is equal to log a naught minus x into b naught divided by b naught minus x into a naught. Therefore, we will get the final equation is 1 divided by a naught minus b naught log a naught minus x into b naught divided by b naught minus x into a naught is equal to kt. This is another form of second order equation when initial concentration of reactants are different. This is also a straight line equation, and this term is dependent variable and the t is independent variable. We can plot 1 divided by a naught minus b naught log a naught minus x into b naught divided by b naught minus x into a naught versus t, and we will get a straight line equation with slope k. So second order reactions graph, as we already discussed, when we plot 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x versus t, we will get a straight line equation with slope k, and the intercept will equal to 1 divided by a naught minus b naught log a naught divided by b naught. This is one of the important determination method for second order of reaction. When we plot this term versus t and get a straight line equation with constant slope, it means this is second order reaction when initial concentration of reactants are different. Similarly, we can also plot 1 divided by a naught minus b naught log a naught minus x into b naught divided by b naught minus x into a naught versus t, and we will get a straight line equation with constant slope and no intercept. Below is example of second order reaction when initial concentration of reactants are different. Summary of today's topic: the rate of reaction is proportional to the sum of the both reactants concentration raised to the power unity. The rate constant unit is per concentration per time, which means liter per mole per second when we represent the concentration in moles per liter. And when we represent the concentration in moles per decimeter cube, then the unit will become decimeter cube per mole per second. Below are integrated equations of second order reaction when initial concentration of reactants are different, which are 1 divided by a naught minus b naught log a naught minus x divided by b naught minus x is equal to 1 divided by a naught minus b naught log a naught divided by b naught plus kt. We can find out the concentration of product or reactant at any t if we know the initial concentration of reactant A and B and also know the rate constant. Similarly, we can calculate the rate constant if we know the initial concentration and the concentration of product or reactant at any T. We can also use this equation for determination order of reaction if we plot this term versus T and get a straight line equation with constant slope. This means the reaction is following second order kinetics when initial concentration of reactants are different, and the slope will equal to K and the intercept will equal to this term. We can rearrange this equation to 1 divided by A naught minus B naught log A naught minus 6 into B naught divided by B naught minus 6 into A naught is equal to KT. Similarly, we can plot this term versus T. We will get a straight line equation with constant slope K. These are some references for today's topic. At the end, thank you very much.